All right, this is Physics 1C for, what is that? This is Physics 1C for February 25th, and today we're going to continue to talk about electric fields. We'll start off with something that's a relatively, I would say, easy problem, and then we'll go back into talking about continuous distributions of charges, and we'll just go from there. Today's class will be relatively short. We'll probably only go for about an hour today. So where's my... Okay, so this is the first problem we want to look at. Okay, accelerated electron. Hopefully you can all read this okay. I'm going to go full screen here. An electron enters the region of uniform electric field as shown in the picture. So we've got these two plates right here, one positive and one negative. Such an arrangement can be produced if you attach a battery with leads going out to two different metal plates. So you've got these two metal plates right here. And they produce a uniform or nearly uniform electric field between the region, pointing up like this. So we have an electron that moves into this region to the right. It's moving with a constant velocity of 3 times 10 to the 6 meters per second. And we know that the electric field within this region is 200 newtons per coulomb, and it points up. And we know the horizontal length of the plates is 0.1 meters from here to here, L. We want to find the acceleration of the electron while it's in the electric fields. We want to find the time at which it leaves the field, and assuming the vertical position that it enters is 0, 0 right here, we want to find its vertical position when it leaves the field. Okay. So take some time to read that and think about it, and see if you can tell me what is the how would we find the acceleration of this electron while it's in the field? Noe's question is, if it was alternating current at the right frequency, would it balance out at the center? So we haven't talked about alternating current. We haven't even talked about current yet. It's a bit ahead of what would happen if it was alternating current, Noe, is that the electric field within this regime right here would go up and then down and then up and then down. And of course, if the electric field points up for some time and then it points down for some time, that implies that at some point there would be zero electric field in here when there was no charge on the plates. That's a lot of stuff we haven't really discussed yet, though, so... But we will. All right, so Delvino says that you can find electric force by taking the charge of the object, in this case an electron, and then multiplying by the electric fields. And then, as he says, then you can say that the electric force acting on this particle is probably the only force. If we think about once the particle gets to this regime right here, let's draw a point like right here, for example, there's going to be an electric force. What direction is the force going to be? I mean, you can kind of see from the picture what the direction of the force is, but what direction is the force going to be?
Towards the negative side.
Okay, and that's because it's a negatively charged particle, and really the right way to write this equation is electric force is a vector, electric field is a vector, you multiply by the charge of the particle. In this case, the charge of the particle we could write as negative E, where E is the electron charge, absolute value of the electron charge. And then you'd multiply by the electric field, which means that if the electric field, here we could write this also as a vector, so this would be 200 newtons per coulomb times positive j hat, so that means that the force that this object's going to feel is going to be down. Okay, so that's the direction of the force. And yeah, and then we can just say, okay, well that's the only force this object is going to experience. Gravity might play a role, but in general gravity is very weak on things like electrons. So once we know what the force on the particle is, we can say that force is going to be equal to the mass of the particle times its acceleration. And since we know what the mass of the electron is, or at least we can look it up, then we should be able to find what the acceleration is. So let's write down all the variables we need for this. So we need the electron charge, little e. That's approximately 1.6 times 10 to the negative 19 coulombs. We also need the mass of the electron, which in kilograms is 9.11 times 10 to the negative 31 kg. This is why the magnetic force is so much bigger than the gravitational force, is because the mass of the electron is incredibly tiny, as I'm sure you already knew. So putting all this together, we'll get that here the electric force should be equal to mass of the electron. Oh, whoops! I didn't do anything there. My bad. Sorry. So replace electric force right here with the magnitude of this, which is E times E. That's what the size of the electric force is going to be, and then we can solve for A. So the acceleration is going to end up being equal to the electron charge times the electric field divided by the mass of the electron. And we can plug all these things in. It's going to be a pretty big acceleration, because this is like 20, 30. You're going to get something like 10 to the 10, 10 to the 12 maybe, because this is times 10 to the 2. What do you get if you calculate this right here?
.51 times 10 to the 13.
Yeah, that's what I got as well. We'll write 3.51, I guess. So that is a massive acceleration. Okay. That's part A. Right? Any questions? Okay, part B. Assuming the electron enters the field at time t, find the time at which it leaves the field. So for this, we need to know something about this initial velocity vector. Now we've already got some axes drawn on here, like this is the x direction, that's the y direction. So this initial velocity that's given right here, I'm going to call that v initial sub x, and it's 3 times 10 to the 6th. Okay, what should we do to figure out part B? The time at which it leaves the field, right here. What can we do to figure that out?
We can use the kinematic equations.
Which one?
Is it distance? Oh, I guess the x component isn't. So we could just use distance equals rate times time.
Yeah, this acceleration over here, it really only points in the y direction, right?
Mm-hmm.
Since the particle is entering with a velocity that's only in the x direction, and the force only acts in the y direction, that means that the particle will maintain this same x velocity as it moves through the field. So like you said, we can just say, okay, well then delta x is equal to the x velocity multiplied by the time. And we know delta x is L, and we want to find t, so we just divide by the x velocity. That should give us the time. What's this going to be?
.3.
Is it times 10 to the minus 8 or 10 to the minus 7?
-8.
Okay. That's what I thought. Let's write one more digit. I don't like doing just 2 digits. Okay, Noe says, since acceleration is in the y direction and we are dealing with electrons, does this mean that since electrons are small enough, we just ignore gravity for now? Yep, that's right. So again, we could calculate what the force of gravity is and the acceleration that it produces pretty easily by just saying if you take the force of gravity acting on this object, and you divide by... Well, this is a silly thing to do because we already know that all objects, I was going to say that we can find the acceleration due to gravity, but we already know what it is, right? The acceleration due to gravity is equal to g, or, negative 9.8 meters per second squared. And then if you want to find the total acceleration, you'd basically add these two, right? But you can see that this number is super, super tiny compared to 10 to the 13. So it makes no difference. Okay, that's the time. All right, and then the next thing we want to figure out for part C, assuming the vertical position of the electron as it enters the field is 0, what is its vertical position when it leaves? What should we do to calculate that?
We can use the now we could use the one of the kinematic equations of like
2D kinematics.
Yeah, like delta S or Y, what have you, equals like V naught T plus 1/2 AT squared.
Mm-hmm. That should work. We should have enough information to use that. Okay, we just found time, so we have this quantity. What's the initial velocity in the y direction of this object going to be, of the electron?
0.
Yep. And we're trying to solve for delta y, so we'll get delta y is going to be 1/2 multiplied by the acceleration that we got in part A, and then times time squared. That'll give us delta y. We can also find the velocity if we want to as it leaves. You can see how much it accelerates. Now we can see that even though this acceleration is really large, the time that it actually spends in this regime is really short because it's moving so incredibly fast to the right. 3 million meters per second. So the distance that it travels here is not going to be super far then, because the time gets squared. All right, what do you get if you calculate this?
(1.91 times 10 to the negative 2).
It's negative 2. Anyone else get the same answer? I didn't hear what you said, actually. Say it again.
1.91 times 10 to the negative 2.
We should be... That's in meters. And that would be basically 1.91 centimeters. Did anyone else get the same answer? I'll calculate it.
Yeah, I got the same answer.
Okay.
Me too.
Great. Really? Wait. I mean, I got something close to that. I got 1.9.
9.4.
4 or 5.
Tell you what, because that last digit's going to depend on where people round, we'll actually just do this. Oops. We'll just write 1.9, because I think we all agree on that. It's really just going to depend on how many digits you kept on this one, and how many digits you kept on that one. Maybe 1.91 is what you get when you don't drop anything. I don't know how you guys did it, but there we go. Pretty basic, like, kind of kinematics problem, and it's connected to electricity, involving a constant electric field, something that this uniform field between two plates is something we're going to be seeing a lot in this class. Okay. So there's 2 other problems I want to do today. How are we doing on time? We're doing really well. Okay. If we have enough time, we're going to do a 4th problem too that will help you with your homework. The question is, do we do this one first? No. Let's do this one first. We'll leave that one for later. Okay, this is example 2114. This is when you're doing your lab manual homework. I know it's not due for a month, but you should definitely try to get started on it. I think the lab manual problem 379, I think, is the number. It's the last problem on your first homework. It's very similar to this. And the techniques we're going to use here, you're going to need to use for that problem. So let me make this just a little bit bigger. All right. So electric field of a dipole. This is something we already talked about. We did a problem where we found the electric field due to a dipole at points like here, here, and here. And now we want to figure out kind of a general expression and look at some of the limits associated with it. So we have a negatively charged particle at a position, well, you can see that there's some distances here. This distance is d. This is the origin, O. And the two charges are separated by that distance, so they're an equal distance away from the origin. So the distance from this one to this one's d over 2. Same thing here. And our goal is to find the size of the electric field at point P. And I'm going to talk about what this P vector means when we get to the end. We call this the dipole moment, but we'll get to that at the end. So we basically just want to find the electric field at point P. And the other thing we're going to do specifically is we want to find the field at a point Y. Okay, so you can see that, I don't know if it's super obvious, but this is this distance here. It's just, we're calling that the Y coordinate from the origin. And we want to specifically find the solution for which Y is much, much larger than D. So really far away, far field. Okay, so to do that, we've already got the direction of the electric field vectors written on here. In case you don't remember, there's a positive charge here. At the point P, there's going to be an electric field pointing away from that point, E+. And then for the negative charge, the electric field at point P will point towards that. So we're going to have two expressions, one for E+, and then one for E-. And of course, we'll just add them together. Both of these are point charges, so we know that the electric field for the positive charge is just going to be K times Q, and we have to divide by the distance between point P and this charge. It's already kind of indicated on here that that's Y minus D over 2. Since this distance between here and here is D over 2, it should be pretty clear that Y minus D over 2 will give you the remainder between this and this. So I'll write that down here in the denominator. And we have to square it. So that's the electric field for the positive charge. The electric field for the negative charge, I'm just going to put a negative sign out here to indicate that it points in the opposite direction as the positive charge. And E- is pointing, and then the distance, in this case, is going to be the distance Y plus D over 2. We'll square that. So the net electric field is going to be E plus E-. So it's going to be equal to save space, I'll put it on the same line. And now what we want to do is we want to simplify this expression. There's different ways that you can do this, but the example is kind of hinting to us. It says to do this, use the binomial expansion. It's written right here. I don't know how well you can read it. What it says is that if I have something that's written like this, a simple binomial, 1 plus x, if it's raised to the n power, doesn't matter what n is. It can be an integer, it could be an irrational number, it doesn't matter, just some power n. As long as the absolute value of x is less than 1, so as long as absolute value of x is less than 1, then to expand this expression, you could write this, it's written here, it basically says 1 plus, you take the power times x, n times x, and then plus, I'm not going to worry about the rest of these terms because we're just going to ignore them. We're really going to basically say that 1 plus x to the n, or 1 plus x to the power n, is going to be approximately equal to 1 plus nx. And this will be very, very good approximation as long as x itself is significantly smaller than 1. So we'll say absolute value x, because it could be negative if you want to, needs to be significantly smaller than 1. If x is a really tiny number or a ratio, then we could just do that, no matter what n is. 1 plus x to the n gets written as 1 plus nx. So what we'd like to do is we'd like to take the expression we have over here, and we'd like to get it into that form, 1 plus x to the n. Okay? So to do that, over a couple steps here, we'll say electric field is, both of these terms have a k times q in them. And I'm going to rewrite both of the terms in the denominator here. I'm going to write them as y minus d over 2 to the negative 2 power. Minus. This one is y plus d over 2 to the 2 power. Negative 2, sorry. Now we need to get rid of this, this y right here. So we're going to factor a y out of each term. If I factor a y out of this expression, here, I guess I'll do it one step at a time. It'll become 1 minus d over 2y with that whole thing raised to the negative 2 power. And then the same thing for this one. Factor a y out. Okay, I'll stop for a moment, let people catch up. Let me know if you have any questions. Next thing we can do is say that we have y to the negative 2 in both of these terms. So we can pull that out to the front. And I don't like writing it like that. I'm just going to write it in the denominator as y squared. Okay. So now what we have is 1 minus d over 2y negative 2 minus 1 plus d over 2y to the negative 2 power. And now I think both of these should meet both kind of qualifications we need here. First of all, in this case, basically the symbol x is basically just d over 2y for our 1 plus x to the n. N is equal to negative 2. And then we look at this and kind of check to make sure that's true. So it says the absolute value of x needs to be much, much smaller than 1 if we're going to use this approximation. So does this meet that definition? D over 2y. If we
Yes.
go, okay, and why is that, Del, you know?
It's because y is much larger than d.
Mm-hmm. Exactly. A point P on the y-axis for which y is much larger than d. So we already know y is much, much greater than d, which means that 1 is much, much greater than d over y. Or we could put a 2 here, and then it's going to be even smaller, right? Okay, so we can expand out our expression using the binomial expansion. So this first term, 1 minus, we basically just take the negative 2 and bring it down in front. So this is going to become 1 minus negative 2 times d over 2y minus. And then this expression, I'll do another parenthesis here because we have the negative sign that's going to operate on all this stuff. 1 plus -2, and then d over 2y. Go down just a little bit. So literally all I did was just bring a -2 down here, bring this -2 down in here, and now we're just going to simplify. So this becomes 1 plus d over y. And then we have -1. And then negative will become +2. Over 2 is just 1, so we just have positive d over y, I believe. And now things are really simplifying nicely because the 1 and the -1 cancel, and the d over y's can be grouped together. So we get a final expression that the electric fields of a dipole on axis is going to be k times q times d divided by y squared. Oh, cubed. Y cubed. That's
D.
one way that it's written. What's up?
Wouldn't it be 2D?
2. Thank you. There's a 2 from d over y plus d over y. Absolutely. Thank you. Yeah, 2. 2kqd over y cubed.
So inverse cubes, that's interesting.
Right, so we know that if you have a point charge, that the electric fields for a point charge, if you're a distance, r away, is given by kq over r squared, so it's like an inverse square law. This goes as y cubed. So if we go back and look at the picture of what we have here, we have a negative charge here, a positive charge here. We're saying the electric field at point P is positive, it points up, and it falls off as 1 over y cubed, as opposed to 1 over y squared, which is what it would do if it was just a single charge. Is that reasonable, that the field of a dipole should fall off faster than the field of a point charge?
Yeah, that's weird.
Why is that?
Well, the electric field lines would be, there would, whatever the field is, it's going to be going to be a sink right by the positive charge. So most of the lines are going to go towards that minus charge. We're not going to have a lot of field lines kind of just away from it.
Okay. What's the total charge of the dipole?
0.
Yep. The total charge of a point charge is obviously just whatever the charge is. So I'd say that's part of the reason why it falls off faster, because there's, the negative charge kind of cancels out the positive charge in a way, but you're still closer to the positive charge. But this still means that dipoles are still going to create a field. It's just going to fall off a lot faster. Now, something that we can do here is we can write this in a different way. So we can define a vector that's called P. And this is called the electric dipole moment. So hopefully that doesn't, it's just electric dipole, and you add the word moment on the end. And the way that this is defined, P is defined as being equal to Q times D. And I don't know the right way to write this vector. I mean, do you put a vector here or something like that? The dipole moment is definitely a vector, for sure. And it basically points from the negative charge to the positive charge. So if you have a negative charge here, you have a positive charge right here, and they're separated by a distance that we call D, which goes from the negative to the positive. We call this D. Then we can define this thing called electric dipole moment like this. And then this electric field can be written as 2kp divided by y cubed. Just another way to write the exact same thing. And this concept of dipole moment, in case you're kind of wondering what that means. Suppose that I have like a polar molecule, and let's say that polar molecule is oriented like this. It's got a negative charge here, and it's got a positive charge right here. And I say that means that there's going to be a dipole moment that points this way. And then, let's say that we take this molecule, so think of it as like a dumbbell with one side positive and one side negative. It could be a molecule, it could be any number of things. It could be a piece of grass or something like that too, that's just charged. And let's say that we subject this to, I'm not going to be able to draw this straight, so I'm just going to draw some vectors in here with this. So let's say that we put this this object, copy, paste, here we go, paste, 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 there we go. So let's say that we place it into a uniform electric field that looks like this. And then in addition to that, I mean, I don't think we have to do this, but let's say that it's that this object is kind of pivoted. Let's say it's fixed so that it can't really move off of an axis that points like this. What direction would the force on the positive charge be?
Towards the right.
And what would the direction of the force on the negative charge be?
Left.
So then what would the direction of the torque be? Clockwise or counterclockwise?
It will be clockwise.
Right. So it's going to tend to rotate like this, right? And how far will it rotate?
Okay, and then... Oh, okay, and then it's going to have to rotate back because it will hit a point where it it overshoots, basically.
Sure. So what you're saying, you said a lot of things there, but I think what some of the things you're mentioning are that it will rotate like this until it basically lines up. I'm just going to use the red vector here. It's basically going to rotate until the p vector lines up to here. But it'll have a little momentum, so it'll go a little bit past that point. But then once it gets past that point, what happens to the direction of the torque?
Reverses.
It reverses, right? Exactly. Which means it's then going to be torqued back up the other direction, and it'll wobble until it comes completely in equilibrium at that point right there, where there'll be no more energy anymore. So it starts off, it has a little bit of energy that's going to tend to rotate it downwards, and then up and back until it basically lines up with the field, okay? So we can make the following statement. If I have some object that's a polar object, right, a dipole, again, it could be a water molecule, it could be all kinds of things are polar. If I have an object like that and I place it into an external electric field, the effect will be that the dipole will tend to line up with the field. Does that make sense? It'll tend to line up with the field. So, yeah, we call that electric dipole moment. I'm never very comfortable with this word, but I do know it gets used quite a bit in engineering to represent torque, I think, or something similar to torque. Is that right? You would help me out with that, those of you that are a little more knowledgeable of engineering? What's the connection between moment and torque in engineering and physics? Anyone know? Have any of you taken like the statics course that they offer here? I think they kind of mean the same thing. Maybe I'm wrong. Maybe you guys can go research that. I think moment and torque are kind of the same idea. Anyway, so yeah, dipole moment. This is the field of a dipole. We call it the far field, I believe is what they usually call it, the far field approximation, because we did make an approximation. It is, however, a good approximation. Yeah, so you have a problem that's like this, and the one that you have, one of the things you need to do is to prove this. You'll have to do this proof, basically. This is the easier one. The other thing you're going to have to do on your lab manual problem is you're going to need to find the same thing, but you're going to have to be like at a point over here. Point P is going to be an arbitrary point that's going to be some distance from the origin like this. And you'll have to find what the electric field looks like here. And that's a little trickier, and some of the algebra and stuff will be a little more difficult, and you'll also have to use some trig functions like law of cosines and law of sines to help you. But it's a really good problem. It's a really good problem that starts with something simple and kind of can get a little more complex. So that's something you'll be working on. All right, we talked about a lot of stuff there. Does anyone have any questions?
Can you explain a bit more why the vector p is pointing in the positive charge direction?
So, why it is that the p points from the negative to the positive like this? Is that your question?
Yeah. Yes.
Yeah. So, okay. Okay. Let me ask a question before I answer your question. Is this why you're getting confused? If I had something like this, where I have negatives over here, and I have, positives over here and negatives over here, the direction of the electric field would go this way, right?
Correct.
Okay, is that why it's confusing you?
Yes.
Okay, the answer is that this is not the electric field. It's a different vector. And in order to make what I said over here true, about how the dipole will tend to line up, the dipole moment will tend to line up with the electric field, that would only be true if we use this type of a definition. So that's my understanding as to why that's written that way. Is so that the dipole moment ends up lining up with the field.
Oh, okay.
I'm gonna give you another example from magnetism to help understand what we said here. What happens when you take a magnet, like as in a compass needle? So I have a compass needle here, and let's say that we label that one side is north, right here. And then let's say that you go to a place where the direction of north is this way. So let's say that that's the direction of north. What happens to the compass needle?
Directed, it will turn clockwise.
It'll turn clockwise, exactly, until it does what? Until the red little piece lines up, right? Like this. Yeah. Can you see how it's the same idea?
Yeah.
So the compass needle is like the dipole moment. In fact, the compass needle has something we call a magnetic dipole moment, and it tends to line up with magnetic field lines, like the Earth's magnetic field. Electric dipoles tend to line up with electric fields. So you can think of a polar molecule, when it's placed in an electric field, as acting like a little compass needle, and it'll basically just point towards... yeah. So that's the reason why.
Okay, thank you.
Mm-hmm. Okay. So, now we're going to go back to doing stuff similar to what we did at the end of last class, where we talk about continuous charge distributions. So this is the one we're going to look at, the electric field of a uniformly charged disk. Now, to do this problem, we're going to need a result from the last class. So last time, one of the things that we did at the end of class it's not letting me switch to this notebook for some reason. What if I go here? I think I just need to close one note and open it again or something. There we go. So this is the thing we did at the end of class last time. The electric field of a uniform ring of charge. And by going through some calculations right here, this is what we got as our answer. Okay? So I'm going to copy this, because we're going to use this. I do want to take a look at this and remember some things before we do it. What did A represent in this equation?
The radius?
Yeah, it's the radius of the ring, right? And what did X represent?
The distance from the center.
Mm-hmm. Yep.
Yeah.
And then Q is just the total charge on that one ring, right? Okay. Uh-oh. I can't switch again. Okay. What if I just, like... Why does it do that? Why can't I just switch? Am I holding something? Oh, maybe I was. I think. Okay. So that was our solution from last time. Let's zoom out a little bit. It's not so big. And we want to use that solution for the ring to solve the disk. So, the way we're going to do this, so here, let's read the problem. It says, a disk of radius capital R has a uniform surface charge density sigma. So sigma is basically the total charge of our object divided by the area of the object. Okay, we call this surface charge density. Calculate the electric field at point P that lies along the central perpendicular axis of the disk and at a distance x from the center of the disk. So very similar to what we did last time, except instead of being a ring, it's a disk. And now it has a surface charge density that's uniform. So the trick for this one will be that you can kind of see it already on here. If we take our disk and we break it into tiny little rings, we know for an individual ring that this is what the electric field is going to look like, right? So if we just add a bunch of rings, right? Add like this ring plus this ring plus this ring, and so on and so forth as we go through the object, we'll eventually get the total electric field. Does that strategy make sense?
Yes.
We did something like this in Physics 1A in order to find the... do it a couple times. So I think we found like, okay. You basically use it to find like the, what's it called? Moment of inertia of a ring. And you use the moment of inertia of a ring to find the moment of inertia of like a donut. I don't know if any of you remember doing that. I don't know if you did it in your Physics 1A class, but it's in the textbook. It's something that, very similar process here. Okay, so all we really need to do is to kind of fix our variables here. So what I'm going to say is that for an individual ring, we're going to produce an electric field at point P. We know that it points along the x direction due to some symmetry and what we saw in the last problem. I'm just going to say for one ring, for a single ring, the electric field is going to be what we call DEX. Okay, so that's just going to be one little cut. It's going to be DEX. And for that, we plug everything in here. So we have K. This is one ring. One sliver, whatever you want to call it. DEX will be K times Q. Now what we'll do is we'll say that contained within this shaded region right here, there's going to be some amount of charge that we call dq. I don't know if you can read that, but that says dq. So that's going to be the charge on the ring. Okay. So we'll multiply by dq here. That's q. The variable x hasn't changed. In the previous problem, x was the distance between here and here. It still is. So we don't have to change the x's. What about a? What should a become now? A previously was the radius of the ring of charge. Can you see on this picture here, what is that radius defined as?
Little r.
It's little r, right? So big R is the radius all the way out to the edge. Little r is the radius of an individual ring. That's the variable that we're going to want to integrate over. Because, we'll start off with a ring that has size really tiny, and we'll move to rings that have size big R, basically. Okay, that was to the 3/2 power. All right. Everything looks okay. I'm really tempted to go look in the textbook and make sure I actually calculated this right last time. But I'm virtually certain that's right. Okay, so that's that. All right, what do we do next? We can't really integrate this, can we? Why not?
Integrating over the wrong variables.
Yeah, so dq would be our variable of integration. So if we tried to integrate this, we'd have a problem that we don't really know the relationship between dq and little r, basically. And to make that maybe more clear, suppose I take a smaller ring. It's going to contain an amount of charge that we call dq as well, but it's probably less, right?
Mhm.
Smaller ring, I mean, in both cases we're talking about rings that are infinitesimally small, so what that means is silly, but certainly smaller ring probably has less charge in it, right? So somehow the amount of charge contained within a ring is a function of the radius, and we need to figure it out. So the trick for doing this is we're going to say that dq is going to be equal to the charge density is constant. This is the charge per unit area. So really all I need to do is multiply by the area of our ring. Right here. And just to kind of pull that ring out a little bit here, the ring that we're talking about has the following dimensions. We know that it has a radius that we call little r. It has a thickness that we're going to call dr. We can't change it to p. What's p, Prince Ali? So the ring that we're cutting out here, this is our ring. It has those dimensions, okay? It has a radius of little r and it has a thickness of dr. And then, of course, the whole thing contains a charge that we call dq. On the whole thing. The whole thing is. Yeah, type out what you mean by that. So what we'll do is we'll say that area that's in there, that area right here, I'm going to call that area dA. It's the kind of infinitesimal area of this infinitesimal ring. Then, if we know what the area of the ring is, and we know that the charge per unit area is constant, if you just take charge per unit area and you multiply by dA, that should give you the amount of charge contained there. Alright. dq equals sigma dA. But to use that, we really need to be able to define what dA is equal to. How can I define what the area of this ring would be?
The circumference times dr.
That's exactly right. So if you take 2 pi r, which is the circumference, that's how long it is around, and then you multiply by dr, that'll give you the area. There's a few different ways to get this result, but that is the right answer. So that's what dA is, and we've got dq right here, right? So let's plug everything in. Going back to our big equation here now. So we have left-hand side is going to just become ex. The right-hand side, we'll put our limits in now that we actually have something to use. So we've got k. dq gets replaced with sigma dA, but dA is this. So that goes right there. Okay, that's the only thing we're replacing, so everything else gets just copied down. Now that we have everything in terms of one variable, remember x is a constant, sigma is a constant, 2 pi, k, etc. Now we have an integral over r. Can you all tell me what would the limits of my integral want to be then? If we want to sum over...
0 to big R.
Yeah. We want to start with a ring has no radius up to a ring that has radius big R. And if we do that, we'll get our answer. All right, so next thing, let us factor out all of the, or pull out all of the things that are constants. So we have, let's see, we'll start with 2 pi k sigma x. And then nothing in the denominator, so that leaves us with just r dr divided by and I think we can just do that integral, right? Because we've got the derivative of the denominator right here in the top. So we could do a... how would you all solve this?
You could do u equals x squared plus r squared,
Yeah.
and then that is just the numerator or the derivative.
Yep. Then du would be equal to 2r dr.
U to the negative 3/2.
All right, so yeah, we don't have to replace this, right? Okay, so let's see. RdR is going to be du over 2. So we'll have in the numerator, it'll become du, and we'll just pull the 2 out here. In the denominator, we just have, or yeah, I guess we can write it like you said, we can just write it as in the numerator. So it becomes u to the negative 3 over 2 du, 0 to big R. Oh, no. Units change, or limits change now.
Yeah, it just changed, but like I mean, you could just substitute them in at the end.
I like.
If you like it, that's fine. Yeah.
I just don't like having no limits. Like I actually don't like them on this one too. It's just you can't. There's not really anything you can put in there. All right, what do we have? So when r is equal to 0, u is equal to x squared.
Mm-hmm.
And when r is equal to big R, u is equal to x squared plus r squared. Equals. So let's see, the 2's cancel. And then this integral, you add
Negative
1
1/2.
power. Mm-hmm. So negative 1/2. And then you add 1 to the power.
Yeah.
Don't you divide by negative 1/2?
Yeah. We divide.
Yeah, divide.
So it's like multiplying by 2, right? Negative 2. So it'll be negative 2 u to the negative 1/2. Let's see, if you take derivative of this, you get this comes down in front and eliminates this. You subtract, yeah, it looks right. Anyone have any problem with that one? Or is that good? Chances are you're all much better at calculus than I am. There may have been a time in my past when I was better at this stuff than you are. That is a long time ago. So I always assume that I'm going to make mistakes in calculus, and you all catch them if you can. All right, e sub x, then, what do we have? So we've got, again, pi k sigma x multiplied by, I guess we can pull the negative 2 out. So we'll have u to the negative 1/2, so that's going to be 1 over x squared plus r squared square root, and then minus 1 over x, I think. Right? X squared to the negative 1/2 would just be 1 over x. And that's the answer. The first question would make sure this actually becomes a positive number, and I think it will, because I think 1 over x is always going to be larger than 1 over this, right? Like this number on the right-hand side is always going to be the larger number.
Yeah.
So that means that, yeah, might make more sense to just distribute the negative inside of here then, so that it looks like this. Just push the negative there and there, like that. And then I'll make them black. So there's our expression. That's the answer. Now I can't say that this is an expression you're going to use super frequently. But it could come up in some problems. I can't remember if it shows up in your homework or not. I do know you have to do a calculation that is similar to this with one change, which is you have a disk, but I believe that the main change is that the value for sigma is a function of the radius. So I think that the problem you have in the lab manual, basically sigma is going to be equal to, I believe this is what it is, I think it's b times r squared, where b is just some constant. And I hope you can see that that's not really going to make the problem a lot harder, right? because look where sigma shows up. It's right here, right? All you're going to do in the problem on your lab manual is you're just going to put the sigma in there. Now you need to show all these steps and you need to be able to explain it and stuff like that, especially if, well, on your homework. But yeah, you're just going to put the sigma in there, and our integral is the only difference is going to be it's going to be like an r cubed, for example, up here. Right? So it's not significantly that much different. It's just kind of just a different type of calculus problem. Now we can. I'll stop for a second and make sure. Are there any questions?
What's your stance on substituting in sigma at the end?
Yeah, we could do that. So in this particular problem, we know that sigma is big Q over big A. Big Q is the total charge, and A is the total area. So technically, it would be pi times big R squared. We can definitely do that if we want to. We can cancel out one of these pi's. Now I'm going to leave it like this because we're going to look at a limit of this, and we want to leave sigma in the answer for reasons that are going to become pretty clear with the next problem that we do. Do I have time for another problem? Oh yeah, sure. I mean, we don't really have to stop right at 3 o'clock. It's 3 now, but we can keep going. I hope. Okay, so what's the interesting limit for this one? Before I just say what it is, what do you think? What would be an interesting limit to look at for our variables x and r right here? What would be something we might be interested in looking at?
Like r becomes real big.
R becomes really big, and why would that be useful?
So it looks like an infinite plane.
There you go, infinite plane, exactly. So a really handy thing here, and part of the reason. Okay, let me write down what you said. So we're going to look at the limit of r getting really big relative to what? It would be x, right? So we're going to look at the limit that r becomes much, much greater than x. That's what we're going to look at. Because that's going to make it so that the disk becomes effectively an infinite plane.
Oh. You get something nice at the end.
You do. It really simplifies really well. Now, why would we want to do this? Well, the reason why is because what we're going to derive is what we started with today. Generally, when we see these kind of setups where you have a big positive plate on the bottom and a big negative plate on the top, actually the electric field inside is going to be given by the expression that we're going to derive right here. We kind of treat these plates as if they're infinite. Are they infinite? No, not really. But if you put them close enough together, they start to look infinite for anything that's contained inside. Because again, if you get close enough to anything, it's going to start to look infinitely big. So, if r is significantly bigger than x, and I can't remember, I don't think we can't just make r 0, right? Because then our answer is 0. Can you all see that? Oh, that's not what we would do anyway, right? Sorry, it's backwards. If r is much, much bigger than x, then we eliminate x squared here, right? So that ex now becomes... What's the best way to do this?
Like you can make r just real big. A term just looks like 0. You just get 2 pi k sigma x times 1 over x.
Yeah. So basically this entire term goes to 0. That works. Yeah, that works. So basically you end up having 0 plus 1 over x. And then what you get, multiply this through, is just 2 pi times k times sigma. There may be better mathematical ways to do this. Like we probably could have just did what we did in the dipole problem. We could use the binomial expansion on this if we want to. But yeah, we get that. Ex is 2 pi times k times sigma. Now we usually write this in an even simpler way. Remember that we have k is equal to 1 over 4 pi epsilon naught, which is this is our other version of the electric constant. And if we plug that in here, what happens is that this becomes this. Oops. Sigma over epsilon naught. So the variable x has disappeared. Obviously the variable r disappeared because it's supposed to be infinitely large. And what this tells us is that if I have an infinite plane, so let's say I draw a plane like this, and we kind of say,
Epsilon naught.
assume that it kind of goes on and on and on forever like this, and then we say that it contains some charge density sigma. And what's charge density? Well, that just means there's a bunch of positive charges right here, all smeared throughout my plate. Then what this says is whether you're above or below this plate, the direction of the electric field is basically just up and away. Like this. You get parallel field lines pointing up like this. And on the opposite side, you get exactly the same thing. The distance that you are away from the plate doesn't matter, although you need to be close enough that it looks infinite, basically. And if you are, then the electric field will be uniform. So this provides a way to know how to produce a uniform electric field. And it also tells us how powerful the field is going to be. It's only proportional to the charge density, so the more charges that you pack within that space, the bigger that electric field is going to get, right? You know what? That's not right. I was like, there's something wrong here. There's supposed to be a 2 here. Because it was 2 pi k. Yeah, I was going to say, like, something's not quite right here. So that should have been, that should be a 2. Sigma over 2 epsilon naught. So now what we can do is we can kind of ask the following question. Suppose that I have a scenario where I have one plate that's right here, okay? And I say this is my positive plate. But I just draw it kind of edge. This is the edge of the plate. So it's going into the board, out of the board, like that. And I say this one has positive sigma. And then I place near it a negatively charged plate, right here, that's negative sigma. We know the positively charged object is going to create field lines that go like this. What direction do you think that the field lines for the negative charge are going to be?
Towards the negative plate.
Yeah, same direction basically, right? Okay. So if I come to some point in between here, like this, point P, and I say, at that point, the electric field due to the positive charge is given by sigma over 2 epsilon naught. And the electric field due to the negative charge, also given by sigma over 2 epsilon naught, because it points to the right. Then the total field in between the plates at point P is going to be equal to just sigma over epsilon naught. So this gives us the electric fields between parallel plates with opposite charge. We actually call this thing a parallel plate capacitor, and it's something that we'll spend an entire chapter talking about it, and I think it's chapter 23? Yeah, 23, I think. We call that a capacitor. It's called that because it kind of has this capacity for storing charges, I believe. So, electric field between parallel plates, just sigma over epsilon naught. Now, you're going to have a homework problem where you have to do things like say, okay, well, what if we have one that's positive 2 sigma next to a plate that's like negative 5 sigma? What's the field in between here going to look like? And it'll ask you to find the field here, here, and here. Okay. So, all you're going to really be doing is using that equation right there. Anyway, I believe that's where we're going to stop today. Anyone have any questions? Okay. If not, then I'll stick around, but I'll stop the recording and I'll see you all next week.